All right, this is going to be the video for Calc 3 15.4 double integrals and polar coordinates. So we're going to introduce the idea of polar coordinate system. I know that this was covered in Calc 1, Calc 2, but we'll talk about how to deal with that with multiple integrals here. So let me share the notes and we'll get going. Okay, so here's a problem. Let's say that we wanted to find the area of this two-dimensional region here that's shaded in brown. And he's got these two rings here. One is defined by the positive y portion of the circle x squared plus y squared equals 1, and this one is x squared plus y squared equals 4, so radius of 1, radius of 2 circle. We wanted to take the double integral of that 3y. So we have some function that varies with y, and we want to take the integral over this region, right? So this is actually pretty hard to do using our current methods. Right. First of all, if you're going to pick a direction of integration, either way, you're going to run into issues. Like if we decide to integrate this way, which let's say we do it that way, well, then in this region from here to here, you have to go from this curve to this curve. But in this region, you have to go from y equals 0 to this curve. And in this region, you have to go from y equals 0 to this curve, right? So it's kind of like there's 3 different regions of integration. And each of them would have different limits of integration. Like in this middle region, well, if you took this equation here and you solved it for y, you would get y is plus or minus, but only the plus version of 4 minus x squared. And then this one over here would be y is 1 minus x squared. And so we would be integrating from the square root of 1 minus x squared to the square root of 4 minus x squared to go from this curve to this curve, right? Let me highlight that with a different color. To go from this curve to this curve, you have to go from this expression for y to this, and then integrate that just from -1 to 1, right? And then in these other regions, like out here, for example, you would have to integrate from y equals 0 up to the top curve, so from 0 to the square root of 4 minus x squared, and then integrate that from 1 to 2. And then there's also a region over here from 0 to 1, from -2 to 1, and then add all of those up. So it could be done. But fair amount of stuff going on. There's plugging square roots in. Luckily, the squares are canceling the square roots. That could have been really ugly if that had not been y to the first, so that it squares and removes the square root. But even with this, we do end up getting an answer, 14, but not super easy. And that's because we have a circular region and we're trying to cover it with rectangular dimensions in x and y, right? So there's actually other coordinate systems we can use, and for 2 dimensions we can define one called the polar coordinate system, which makes it easier to do integration if you have circular elements. So the way we do polar coordinates is, you have to go from the origin to a particular point in the domain x, y, right? And one way to do that is to go a distance in the x and a distance in the y. Right? But it would be just as good to define it as a distance directly to the point at some specified angle and standard position. And so when we use the distance, the radius, and the angle theta to define the position, that's called using polar coordinates, distance from a pole, which is the origin. And so to convert from rectangular to polar, we know that the radius is just the square root of x squared plus y squared, where x and y are the x and y components. And the angle is the inverse tangent of the opposite over adjacent, the y over the x. And to go from polar to rectangular, we know that just like we did with vectors, right, the x component is the radius times cosine theta, and the y component is the radius times sine. So as long we can use these standardized formats, as long as theta is always defined clockwise from the positive x-axis, as it always is for trig and calculus. All right. So what we're going to find is that if we instead express our domain using r and theta instead of x and y, that previous region to integrate over, which was circular, is much easier to do using this than rectangular. But we have to know what dA is, right? In rectangular, dA is dx times dy. It's a little rectangular element, dx, dy. So that's really easy. But is it that simple when we go up to dA, or to r and theta, to polar? Okay, well, it's still going to be a little region here, right? But the region is, it's not perfectly rectangular. Instead, it's a change in each of the variables. So there is a radius, and there's a little change in radius, dr. So that's kind of like one dimension of this sort of semi-rectangular area. Right, but this other dimension, the width, is not really, it's not perfectly rectangular, but approximately rectangular. That's really an arc length, right? An arc length is r times d theta, right? Because an angle defined in radians is the length divided by the size of a radii to convert it into number of radii, right? So arc length is r d theta, and that means that this arc length is r d theta, and so this area is approximately rectangular, with dr this way and r d theta this way. So you would have to take r times dr times d theta, and that would be the area element that corresponds to taking dx times dy for rectangular. So a little bit more complicated, we have to multiply by this r. Right, so when dr and d theta are infinitesimally small, the area is approximately rectangle, so we define dA to be r dr d theta. Now, Miss Dastu, when she taught this section, she has a like a pirate hook that she would hold up, and she would say, to remember it, just remember that it's r dr d theta. Like, imagine you're talking like a pirate. So if that helps you to remember it, by all means, picture a pirate, and it's r dr d theta, right? That's we have to have some way to remember the structure for dA. Okay, so it's r dr d theta. And that means that when we want to do this this integral, right? Well, we're going to still have the 3y, right? That's the integrand. But we know that to convert, x is r cosine theta, y is r sine theta, and that means we're going to replace this y here with r sine theta, okay? And the dA here is going to be replaced with r dr d theta, right? So we have to do some substitution in here instead of doing dx dy. And we usually have our function expressed in terms of x's and y's, so we have to substitute out the x's and y's to convert them to polar coordinates. The other thing we have to do then is come up with new limits of integration. So the new limits of integration here, it doesn't matter which one we do first. Let's say we put r first, okay? Then that means these are r values, right? But this is where it gets much easier. Instead of all that square root stuff, right, we're just going from radius 1 to radius 2. So now these just become numbers from 1 to 2. And then the angle has to be the angle in standard position. So this is where theta would be 0. This is where theta is equal to pi over 2. This is where theta is equal to pi. And so to cover this entire region, we have to go from 0 to pi. And that's where we get the theta limits of integration here. Okay, so we get simpler limits of integration. And this is a factorable integrand, right? We can separate the thetas from the r's. So we can do the theta part separate over here and take the integral from 0 to pi of sine theta d theta. And then we can take the 3 outside, that's a constant. And then we have an r and another r. So one r and another r is r squared dr. And so that would just be 1/3 r cubed. And we're integrating from 1 to 2. Right? Over here, the antiderivative of sine is negative cosine, integrated from 0 to pi. And so we plug in the pi and the 0 and the 2 and the 1. And we end up getting 14 with a whole lot less steps than it took in rectangular. Remember, this is what it looked like in rectangular. This is a whole lot easier in polar. So basically, polar makes our lives easier. And it's whenever we have circular regions, or regions where the boundaries are circles. That does happen very frequently, though, so it turns out to be a very valuable tool in certain instances. All right, so that's polar coordinates and how it can help us. Now, in this case, we happen to have integral limits of integration that were fixed. They were constants. In other words, the radius went from always from radius of 1 to always radius 2. And the angle was from a constant to a constant, right? But as you might imagine, there are times when the inner function might be a dependent on the variable of the outer function. That's true. If we have a general region, then if you want to do r first, right, you're integrating r first, that means that you have to express this boundary as a function of theta, and then the other boundary as a function of theta, so that you're going from some function of theta to some function of theta and getting some expression of theta when you do the integral. right? And then when you do the outer integral, you finally integrate with respect to the region of theta, and then you have to cover the entire region, whatever the lowest angle is to the highest angle, always from lowest to highest. And it could be the other way around too, right? You could decide to integrate the theta first. This isn't typically done because the dA element has an R already in it, but you could integrate the theta first and express these boundaries as functions of R, and then integrate that way, and then start at some low R and ending at some maximum R, right, to cover the shaded region. So we still can have things where the inner integral is a function of the variable of the outer integral. Okay, so that's really it. We're just going to look at some examples now to see how it works. And it's the kind of thing we really have to practice. It can be either very straightforward or extremely challenging, just depending on the nature of the problem. And same thing, the integrals themselves can be really challenging or very straightforward. So in general in the class, this is a class about multivariable calculus. So we're not really testing you on your ability to integrate. You can use integral tables. You can use, you can do things by hand. We'll typically ask you to do it by hand every once in a while, when it's simple, just to keep those abilities current, right? But when it gets really tough, we'll resort to tables or technology to be able to get the integrals. All right, so sketch the region and then evaluate this. So we have this integral. It's already in polar. So I'm just going to go ahead and sketch it in polar. So we have my xy here, right? But I'm talking about particular regions. So let's see. Well, we have R this is R equals 0, and this is R equals 4 cosine theta, right? So I think what I'm going to need to do is maybe make a little table to see what's going on here. Let's make a little table. So let's try some different theta values. I know what R is 0 is. That is a point, right? So that's this. But what is R equals 4 cosine theta? So to graph that, I'm just going to pick some thetas and plug those in by hand to figure out what the radius would be at those angles. So if I pick 0, I'm going to get 4 times the cosine of 0, which is 1, so that's 4. So that means that when I have the angle 0, theta is 0 radians, then I'm at 4. 1, 2, 3, 4. So here's a dot that's on this curve, this outer curve. Okay, let's see. How about pi over 6 is the next special value. So 4 times the cosine of pi over 6, that's 4 times square root of 3 over 2, which turns out to be about 3.6. Okay, so if I'm at pi over 6 as an angle, then I don't go all the way out to 4. I go to about 3.2, so maybe there. Okay. Next kind of special angle is pi over 4. So 4 times cosine of pi over 4 is 4 times the square root of 2 over 2, which turns out to be 2.83 when you plug it in a calculator. So if I go to pi over 4, which is like the 45-degree line, maybe I should use a different color. Let me put these things on here and then do a different color. Here was a point, here was a point. Okay, so now we're down to 2.8. So this was 4 out here, 3, 2.8, maybe right about there. Okay. All right. And then at 2 pi, or pi over 3, sorry, pi over 3, we would have 4 times the cosine of pi over 3, which is 4 times 1/2, which is 2. Right. So if I were to go to pi over 3, then only this far out, 2. And then finally, when I get up here to pi over 2, I have 4 times cosine of pi over 2, which is 0. And so I'm back to 0. So it looks like, let me actually now show this. This is the upper curve, and then the lower curve is just this point here. So I believe the region we're talking about is this region here, right? There's a sketch. So it's quite a bit even to sketch this region, but we're trying to integrate this. It just has an integrand of 1, which is going to give me the area in this region right here. Okay. All right. Yeah. And then we're then integrating in theta from 0 to pi over 2. So that means we're not going to continue this red curve past this point and make like a rose or something like that. We're going to stop at that point. So this is the complete region from 0. So the boundaries are, we start integrating at 0 and we stop integrating when we get to pi over 2. So this is indeed the region. Okay, so that's the sketch. That was the hard part. Now we're going to do the integral, which is actually easier, I think. We'll see. Is this separable? Well, not really, because I have a non constant integration. So I'm going to have to do this integral first. So first the integral. This is going to be the integral from 0 to 4 cosine theta of r dr, which will be 1/2 r squared from 0 to 4 cosine theta, right? Which is going to be 1/2. We're going to get 16 cosine squared minus 0 squared, right? When I plug in these expressions for r. So this is going to end up being 8 cosine squared theta. Okay. And then let's do the outer integral. The outer integral is the integral from 0 to pi over 2 of that 8 cosine squared theta, d theta. So I would either look this up in a book, or I could use a trig identity. There's a trig identity. Cosine theta is 1 plus cosine 2 theta over 2, which means I could make this the integral from pi over 2, 8 out here. Cosine squared is 1 plus, it's 1/2 plus 1/2 cosine 2 theta, d theta, right? Which means I could bring the half out here too, and I would get 4 times integral, let's see, of just 1 d theta, and then I've got 4 times integral from 0 to pi over 2 of cosine 2 theta d theta. Maybe I could do a little u sub here. U is 2 theta, so du is 2 d theta. And so this integral here could be rewritten as the integral of cosine of u, and then the d theta would be 1/2 du. I'm going to move the 1/2 out there. And then I have a new limits of integration. So if theta is 0, then u is 2 times 0. And then pi over 2 times 2 would be pi. So then I'm going to have the antiderivative of cosine, which is negative sine. No, that is not negative sine, it's sine. It's sine from 0 to pi, so it's going to be 1/2 sine of pi minus sine of 0, but both of those are 0, so this whole thing is 0. So we end up with the outer integral is, let's see, this is going to be 4 times the antiderivative of this is just the angle, 0 to pi over 2. That would be 4 times pi over 2, or just 2 pi, all right? And then plus 4 times 0, so the whole thing ends up being 2 pi. Yeah, this is probably on the upper limit of what I would just do by hand. Could we just do that in a calculator? Yeah, we could do that in a calculator, I suppose. Yeah. All right, so probably the most interesting thing here was the graph, right? All right, let's take a look. Now, for the rest of them, we're going to be looking at, well, let's actually do, one more evaluation. Let's do this one. Sketch the region and evaluate. All right, so we want the double integral of this function. So we want to integrate the values on the surface, but only over a region, and the region is defined by this. So first we'll have to start by sketching the region. So we'll start by sketching the domain. And one of these, this appears to be, this is like a circle. This is a circle with radius 2, right? So if I go out here to 2, radius 2, and draw a circle, okay, and it's all the places where the r, this is really what we're saying is, in fact, maybe I should explicitly state it that way. This left side of this expression, x squared plus y squared, is r squared. And if r squared is less than 4, it means r is staying less than 2. So it's all this region inside this dotted circle, but also only the places where x are 0 or positive. So I believe it's this region right here. Oh my gosh, let's use the green. How about this? This is the region. All the places where the radius stays less than 2, but only with positive x's. So this is the region here. So now they didn't tell me, they didn't convert this for me, they didn't tell me so what to use for dA. So we'll have to do all that by hand. We're going to use our x, our r. Well, x is r cosine theta and y is r sine theta. So let's do some manipulation here. This is the same as 4 minus x squared plus y squared, right? But because x is r cosine theta and y is r sine theta, let me prove why I asserted that x squared plus y squared is r squared. If you did that, if you did x squared plus y squared, you would get r cosine theta squared plus r sine theta squared, which is r squared cosine squared theta plus r squared sine squared theta. But you could factor out the r squared, get cosine squared plus sine squared, and that by trig identity is 1. So that's why this is true. I've memorized that as a result, but we should probably see it once. And so that's going to allow me to take this and replace that with r squared. This is the same as the square root of 4 minus r squared. So now I've converted the integrand to polar. The dA is going to become r dr d theta, right? So I've got my integral is the square root of 4 minus r squared, r dr d theta. And then the last thing is I have to figure out the limits of integration. So let's do the r on the inside. So this is nice, right? We're going from a radius of 0 out here to a radius which is always 2. Doesn't matter the angle. So this is just going to be 0 to 2. And then the angle for theta, well, let's see, the lowest theta would be, theta is negative pi over 2 all the way around through 0 to theta equals pi. You always want to make this limit of integration monotonically increasing. So this has to be from a low number to a high number and not jumping around or having gaps. So that would be the appropriate setup. And now we can go ahead and integrate this. Let's do the inner integral first. Actually, we can separate these, I think. Yeah, these can be factored. So let's do this. We'll take the integral from negative pi over 2 to pi over 2. There's no theta anywhere in here, so this is just d theta. But then separately, we can do this, square root of 4 minus r squared r dr. And this one, well, this one over here is really straightforward. It's just theta from negative pi over 2 to pi over 2, which becomes pi over 2 minus a negative pi over 2. So it's going to be pi over 2 plus pi over 2, which is pi, right? So that's this factor. And then this factor, we're going to be able to use u substitution, I think. If we make u 4 minus r squared, then du is negative 2r dr, which means r dr, this, is equal to negative 1/2 du. So I can resubstitute this and make this the square root of u, or let me write it as u to the 1/2 square root of u. And then the r dr is negative 1/2. I'm going to print the negative out, negative half here, and then du. Okay, so what's my new limits of integration then? So if r is 0, then if I plug it in here, u is 4. And if r is 2, then I get 4 minus 2 squared, which would be 0. So this is going to end up being negative 1/2. The antiderivative here would be 2/3 u to the 3/2 evaluated from 4 to 0. So we're going to have 2/3 times 0 to the 3/2 minus 2/3 times 4 to the 3/2. This is 0. And 4 to the 3/2 is 8. So we're going to have 8 times 2. So that's going to be, let's see, 8 times 2 divided by 3. And then that's going to be negative multiplied by a negative 1/2. It's just going to give me 8/3, positive 8/3. So this number here turns out to be 8/3. And so our final answer is 8 pi over 3. All right, so that wasn't too bad. So be on the lookout for x squared plus y squareds. Those become r squareds, right? And this was nice because we ended up with constant terms here, so I was able to separate the factors. All right. I want to just do three more things for you, but we're not going to actually do the integration. I'm just going to do the sketch and the setup for you. These are homework problems, actually. So I'd like to show you how to set them up, but then I'll ask you to do the integration steps yourself. All right, so let's do this one. The double integral of x dA, where d is the region in the first quadrant that lies between the circles x squared plus y squared equals 4 and x squared plus y squared equals 2x. All right, so let's make a sketch. Well, first of all, this one is a radius 2 circle centered at the origin. Would you agree? So I can go ahead and add that. Make it pretty big here. Radius of 2 circles centered at the origin would be this. Okay, wait, I want to have a different color there. This. Okay, that's this right here. This is also a circle, but I'm going to have to complete the square to find out what its region or where its center is. So let's do a little completing the square procedure. So x squared minus 2x plus y squared equals 0. If you completed the square here, I could leave a little space here to complete that square. This is already y minus 0 squared equals 0. So we really want this to be x minus something squared. So what I could do is take this -2 and divide it in half and get -1, square that, and that would give me +1 here, but I have to balance the +1 I added here with a +1 over here. So that's to complete the square procedure. And so that means that I have a radius 1 circle, but the center of this circle is at 1, 0 instead of the origin. So let's draw that. Let's do it in red, actually. So the center of this circle is 1, 0, and its radius is 1. So this is this circle. We had to complete the square to do that. Okay, now what is the region? The region is only in the first quadrant, and it has to lie between the circles. So this is the region that they want us to find the integral over. And not just of the area, but of the integral of x. So it's varying that what we're summing up. So this is the region. So that's the sketch. And now we need to set up a, we'll set up an integral. So we are going to use polar. We have circular elements here. So to do that, first of all, we're going to take this x here and replace it with r cosine theta. And the dA is going to be r dr d theta. And now we have to figure out the radiuses and stuff, right? So let's put an arrow on here that indicates what we're doing. We're going to integrate radius first, which is typical, and then we'll do the angle at the end. So I'll use a black arrow for that. That means that we're integrating, for example, from here to here, right? At any particular angle, we're integrating starting here and stopping here. So we need two expressions here for the radius in terms of the angle, right? So the red equation is x squared plus y squared equals 2x, right? Let's convert that to polar so we can get this in terms of r's and thetas. We know that x squared plus y squared is r squared, and we know that x is r cosine theta. So this is, if we were to get everything on the same side, r squared minus 2r cosine theta equals 0, we could factor out an r, and it would be r minus 2 cosine theta equals 0, which has two solutions, r equals 0, which is trivial, or r minus 2 cosine theta equals 0, which means r equals 2 cosine theta. So in fact, that is what this edge is. On this edge, r equals 2 cosine theta. So if I plug in a theta value, this tells me how far out I am. Okay. Now the blue one, we could do something similar to. For the blue, we have x squared plus y squared equals 4, which we know is r squared equals 4, which would just be r equals plus or minus the square root of 4 is plus or minus 2, but r's are never negative, so this is just r is always 2, which we actually already knew, right? I didn't have to do that. So r equals 2. And that means that my lower limit of integration here is going to be 2 cosine theta for r, and my upper limit of integration is going to be 2. And then I need to figure out, okay, what are the lowest and highest angles I have to go to cover? So I have to start here at theta equals 0, and I have to go all the way around until I stop when theta equals pi over 2. So the limits of integration for theta would be 0 to pi over 2. So that's the setup for problem 14 in the homework. And then I'd like you to go ahead then and actually do the integral. And this one I think you should be able to do by hand. Okay. Maybe not. Give it a try. Let's take a look at number 15. This is also in the homework. Use a double integral to find the area of one loop of the rows r equals cosine of 3 theta. And we're just going to do the setup, and Hobby do the evaluation for homework. So since we're finding an area here, the integrand is just 1. Okay, so all right, let's make a sketch. Same thing, we'll try to sketch it. I think we're going to have to resort to a table to even sketch this. Yeah, let's make a little table over here. So at different thetas, what is cosine of 3 times theta? All right, when we use 0, actually, I guess I need less space there. How about like this? Cosine of 3 theta. Okay, when theta is 0, then r would be cosine of 0, which is 1, right? Okay, when theta is pi over 6, this would be cosine of 3 times pi over 6, which is going to be cosine of pi over 2, which is going to be 0 actually, right? All right, so let me start kind of graphing these. At 0, I am at 1. Okay. By the time I get to pi over 6, I'm at 0. All right. You know what? I think I'm going to have some at least one intermediate value. What is it if I go to pi over 12? What's happening in between there? Let's try that. Pi over 12. Cosine of 3 pi over 12 would be pi over 4, right? Which would be the square root of 2 over 2, which is about 0.7. So yeah, it looks like I'm at 0.7 here, so 0.7. So yeah, so I think what's happening is we're starting here and we're going like that, kind of along that path like that. Okay, and let's keep going. It says one loop of the rows, so I haven't completed a loop yet. If you keep going here and you try other values, like say pi over 4, that's cosine of 3 pi over 4, which turns out to be negative 0.7. And if you go to pi over 3, you get cosine of pi, which is negative 1. So it takes all the way over to pi to get to negative 1. So what happens is this will, because of this 3, it's actually going to look like this. If you carefully look at all these different things, you're going to get something that looks like this. Okay, this is called a rows. Those are actually symmetrical. But to get one piece of rows here, it says one loop of the rows. That's going to be defined as one of these enclosed areas like that. Okay. All right, so to set that up, well, let's see. I need to have a double integral. The integrand is 1 because I'm interested in just the area. We're going to do r d theta. And let's see, we would be going from, let me get a black arrow. We're going to be going from 0 to the edge. And the edge is defined by this. So I don't have to do any kind of fancy stuff to get that. This is just going to be from 0, r equals 0 to r equals cosine of 3 theta. The harder thing is figuring out the limits of the angle. So we never go beyond pi over 6. And since we have to go over here to just get one continuous integration, we should start at negative pi over 6. So let's go from negative pi over 6 to pi over 6 to cover that one region. So that's going to be the setup for number 15, and I'll let you try to do the integration. And you can try these on your own too. Since you're watching the video, you can pause these. One more setup. This one's particularly challenging for number 25. What's the volume above the cone z equals square root of x squared plus y squared, but below the sphere x squared plus y squared plus z squared equals 1? All right. So this is actually three-dimensional, which normally we don't do that in with double integrals. We use triple integrals, which we're going to talk about in the second half after the test. But let's kind of sketch it. We can actually accomplish this particular one with a double integral. So first of all, we have a sphere, and this is centered at the origin 0, 0, 0 with a radius of 1. Right, so I have a sphere, three-dimensional sphere. Okay, and then there's a cone, and the cone, I'll use red. The cone looks like this. Okay, so what is the region, the volume we're trying to find? Well, it's above the cone but below the sphere. So basically, imagine if you had a snow cone that was totally filled, like the snow cone paper was filled, and also the rounded part up here, kind of the snow cone shape. We want the volume in that. All right, how are we going to do that? Okay, well, we're going to convert it with a double integral into something which is in a plane. So imagine if we took an xy plane, like a cut through this, okay? Like we just stayed in a particular region like that, right? We can cover that region with polar coordinates, okay? So if we did that, maybe I can draw it down here in the xy. We would have circular cross-section here, right, at some particular height. And of course, these, as we go up in z, these would increase, right? The radiuses would increase. But we're going to first cover this area in polar. Okay, so what would establish the boundary for that? Well, let's see. We would have to have a region here. So the cone is establishing this edge here, right? And we know that in this case, it's z is the square root of x squared plus y squared. But that we know that x squared plus y squared in polar is r squared. So that's really saying z equals r. So the radius of this circle just depends on whatever the z is. Okay. So how could I do that? Well, I think I could just say, okay, on this edge here, z is equal to r, right? And then imagine that I'm taking a volume element. So imagine that I'm going to integrate something like a piece of this, like this, right? A volume chunk like that, right? The bottom would be r dr d theta in the domain here, r dr d theta. And then the height would be dz, right? So the volume of this little box element is going to be r dr d theta times a change in height, dz. So I'm trying to make a double integral do the work of really a triple integral, where we have a third variable. So what would be the change in height here? right? I'll actually call it delta z because it's a large change. Well, at this place, z, we have the sphere, right? So you could say if I solved this for z, I would have the square root of 1 minus x squared minus y squared. And this lower limit here is set by the cone, where z is equal to the square root of x squared plus y squared, right? So while we're here, the z we just showed down here is equal to the square root of r squared, and therefore z is equal to r. And up here, the z would be equal to the square root of 1 minus r squared if you factored the negative out. So this difference here is just going to be take the top z value, 1 minus r squared, and subtract the bottom value, r. So if I integrate this, r dr d theta, but times this square root of 1 minus r squared minus z, I get a third dimension in here for free. All right, so let's use that to try to build the integral. It's going to be a double integral. I've got this square root of 1 minus r squared minus r in there. Okay. And then times r dr d theta to pick up the area inside the circle. And then now we have to decide what the radiuses need to be. So the radiuses, well, actually, we're just going to go from, it's getting kind of crowded here, but let me use maybe, I don't know if this will work, but I'm going to go from here out to here to establish that's the first integration. So it's just going to go from r equals 0 to r out here on the edge, right? And that's going to be wherever the intersection of the cone and the actually, I should probably have drawn it this way. Do it this way. What's going to stop this radius is when we get to the edge of the cone, and the maximum radius is going to be set by this distance right here. So that's the r is going to start at 0 and go as far as this radius right here. The question is, what's that radius? Well, that radius is the radius at the intersection of the cone and the sphere. So, okay, let me do an intersection calculation. The intersection would be whenever both of these two are solved simultaneously as a system. So what I'm going to do is I'm going to substitute this z in for that. So if I have x squared plus y squared equals, or wait, x squared plus y squared plus z squared, where z is the square root of x squared plus y squared, that gives me x squared plus y squared plus, those things cancel, another x squared plus y squared equals 1, which is 2x squared plus y squareds equal 1. Right, which means 2 times r squared equals 1, right? Which means r squared would equal 1/2, which means r would equal plus or minus 1 over the square root of 2, square root of 1 over square root of 2. And since r is never negative, it means we're going from r equals 0 to r is 1 over the square root of 2. That's the maximum extent of r. And then to cover all the way around, we're going to go from theta equals 0 all the way around back again until theta equals 2 pi. So from 0 to 2 pi. Here's the setup that would be required to find the volume in that snow cone shape. Well, that's pretty intense. We're going to have a much better way to do that after we talk about triple integrals in the second half of this unit. As always, at first, the techniques are cumbersome and we try to extend them, but then we have a better way later. All right, so with that introduction, go ahead and give this a try. Try the homework, and hopefully you'll be successful. Bring questions to tutoring or to class.